3.5 talks about an application of derivatives. Derivatives are really rates of change. So when we find dy dx, which is the first derivative, that tells us the change in y over the change in x. So derivatives are a way to measure how different physical properties change. For example, distance over time. When you're driving in your car, you're going a speed, and the speed is usually miles per hour. Miles is a distance, and hours is a time, and that tells you how far you travel in 1 hour of time. It tells you how your distance changes over a certain amount of time. And the derivative can help us find that. So the velocity is thought of as the change in position over change in time. And the thing about velocity is it's something called a vector. That means velocity can have a direction to it. And you can have positive velocity, which means a lot of times that you're going to the right or you're moving up. And you can have a negative velocity, which could mean that you're moving to the left or you're moving down. A lot of times it's the reference frame people will put on it. But the average velocity is really the slope, where to find your y values you got to plug it into the position. For example, on the interval AB, so that's a time interval, from the time t equals a to t equals b, start and stop. To find the average velocity, you take the position that you end at minus the position that you start at, that's the distance you travel, and the time you ended minus the time you started, that's the amount of time you traveled, distance over time, which is really a slope. F of b is the position at b, because f is the position function, and f of a is the position where you start in a, over b minus a. So these are called secant lines when you look on graphs for the slope. So here's an example of a problem that has a graph. For the following figure, it shows the position function of an airliner on an out and back trip from Seattle to Minneapolis, where the f of t is the number of ground miles from Seattle t hours after takeoff at 6 in the morning. The plane returns at 2:30 p.m., which is 8.5 hours later. And part A says calculate the average velocity of the airliner during the first 1.5 hours. So that means t equals 0 to t equals 1.5. So what I do is I literally calculate the slope of the line that starts at t equals 0 and ends at t equals 1.5, which is right here. So if you think about it, this is called the secant line, and it's the line that connects these 2 points on the graph. That line has a certain slope, and the slope of that line will be the average velocity, because the change of position is the y, and the change in time is x, and that's what average velocity is, change in position over change in time. And that's slope, dy over dx. So for part A, we have time 0, and we got to figure out what the position was then. Well, the position function, if you look at time 0, the y value there, the position, is 0. So I start at 0 hours, and the position is 0 miles from Seattle. And then I got to figure out what happens at 1.5, which is the ending time. So at 1.5 hours, the position at 1.5, we can tell by looking at the graph. This must be 600. So this is the point 1.5, 600. The y value is 600 miles from Seattle. So the average velocity is the end position, which is 600 miles, minus the start position, which is 0 miles from Seattle, over the end time minus the start time, and these are hours. We don't usually write the units in. I am here just so you can see where the units are coming from. So I get 600 miles over 1.5 hours, and you divide those numbers to figure out exactly how far you traveled. 600 divided by 1.5, it's 400. So the average velocity is 400 miles per hour. And that's for the first hour and a half of the trip. To do part B, we have 2 different points to look at. In part B, it's between 1:30 and 2:30. That's 7.5 to 8.5. So we have to look at 7.5 hours from Seattle, and we have to look at the position there. And we have to look at 8.5 hours out of Seattle. And we have to look at the position there. So we'll draw the points on. Here's 7.5 hours. Right about here, we'll say. And here's 8.5 hours. So the blue line represents the line whose slope we're trying to find. And that'll give us the average velocity over this period. We'll notice at 7.5 hours it looks to be about 200 miles. And at 8.5 hours it looks to be 0 miles again. So the average velocity is the end position, 0 miles from Seattle, minus the beginning position, over the end time, minus the beginning time. So you get negative 200 over 1 miles per hour. So you'll notice the velocity can be positive or negative. In this case it's negative because the distance it travels, the position looks negative. It's actually approaching Seattle again. And we're measuring this from where Seattle is. So that's A and B. They have to do with just calculating the slope using the graph. At part C it says, when is the velocity 0? And if you look here, when you figure out where the velocity is 0, what you're doing is you're looking for where the slope of the line between 2 points would be 0. Right? Notice we had 0 and 1.5. And we looked at the slope between that line to figure out the velocity. So where in this graph would we get a line that has slope 0? Remember, a line with slope 0 is a horizontal line. And that happens all through here. Notice if I draw a line that touches the graph, a tangent line, that whole time it's slope 0. It looks like it happens about 2 3/4 hours to 5 3/4 hours. Because the slope of the line is 0, which means the position doesn't change. The position from Seattle is about 1,500 miles. That's 14. So this is 15. So from 2 3/4 hours to 5 1/4 hours, the position doesn't change. So when I calculate the top of this, the position it'll be 0, because the position is the same, 1,500 miles from Seattle over that time. So between 2 3/4 and 5 1/4 hours, it looks like, is where part C is. From Seattle. Could be it's a layover there, or the plane just stops for maintenance and turns around. And then it says, determine the velocity of the airliner at noon and explain why it's negative. So at t equals 6, this is at noon, the reason the velocity is negative is the tangent line is what gives us the velocity at a specific time. But if you'll notice, at 6 they're traveling back to Seattle. So when I subtract the top, I'm going to get a negative number as time moves to the positive direction. Or you can look. If you look between the slope between any 2 points, you're going to get a line with a negative slope. So that's the idea between a graph. You can also do it with equations. So instantaneous velocity is the velocity of an instant. What we were doing before was a velocity between 2 points. They give you a velocity function. Sometimes you plug it in to figure out the y value. Sometimes you can look at a graph. But there's also instantaneous velocity, which is the derivative. That's what the derivative gives us. The velocity is the limit as I move a little bit to the right of t. If you look at the graph here, if I want to find the velocity at 6, I'm going to move a little step to the right, which I'm going to call h. And this point here is going to be 6 plus h. And so that means the y value of that point is f of 6 plus h. And so what I'm doing with this equation is I'm moving a tiny step h to the right and calculating the limit as h goes to 0. Because once h goes to 0, these 2 points will line up on each other. If h is 0, then 6 plus h and 6 will be at the same place. I'll find the velocity at a specific point. So I take the derivative. What this turns out to be, by definition, is the difference quotient, which gives me the derivative. So to find the velocity, I take the position function and find the derivative. And that's how the distance changes over time. To find the acceleration, that's the derivative of the velocity, which is the second derivative of position. And that's how velocity changes over time. So when you hit the gas and you go from 0 to 60 in 2 seconds or 3 seconds, that's an acceleration and you feel it in your body. So position has distance units, and velocity, that's going to have a distance on top and time on the bottom. These are for the units. And acceleration has velocity units on time, or distance units on time. Distance units on top. And time units squared on the bottom. Like feet per second squared is a velocity. And so we're going to use the derivative to find velocity and acceleration in the next problem. This one here says it gives me a position function. So this function right here describes where in space the object is, how tall it is off the floor, or in this case it's moving left and right. So I plug in t and I figure out where it is from its start position. T is the time. So find the velocity and acceleration. To find the velocity, I just need to take the first derivative. The derivative of the position function gives me the velocity. Well, I'm going to find the derivative using our techniques. The derivative of 18t is 18. The derivative minus 3t squared becomes minus 6t. That's the velocity. To find the acceleration, I take the derivative of the velocity, and that's just negative 6. Now, they didn't give me units here, so I can't put units down on my acceleration or velocity. Notice that negative 6 is the second derivative of position. So part B, it says, when is it moving stationary left and moving right? Well, if I can figure out when it's not moving at all, that's when the velocity is 0, I know it's not moving left or right. So first I'm going to figure out where the velocity is 0, and then I'm going to check points around it to figure out if it's positive or negative. If the velocity is positive, it's moving right. If it's negative, it's moving left. So the first thing I do is I take the velocity and I figure out where the velocity is 0, where this thing has stopped moving. That must be where it turned around. So I get 18 equals 6t and 3 equals t. So I know at time 3 seconds the velocity is 0. It quits moving. So when I try to figure out when it's moving right or left, I know at 3 seconds it's not moving either direction. It's not moving at all there. So now I can test around 3. I can use the points 4, and an easy one on this side would be 0. And I'm going to plug them in and see what I get for the velocity. Because moving right or left is the velocity there. If it's moving right, the velocity is positive. If it's moving left, the velocity is negative. So I take the number t equals 0, and I see what the velocity is there. And it turns out to be 18. That's a positive number, so I know at 0 it's moving to the right. Then I take t equals 4 and plug it in. Into the velocity. 18 minus 6 times 4. Let me write this somewhere where we can more clearly see it. I also have t equals 4. The velocity at 4 is 18 minus 6 times 4, which is 18 minus 24, which is negative 6. Check. These blue points are where I check to see which way the velocity is moving. I notice at 4 the velocity is negative. So that means it moves right where the velocity is positive. Notice it starts at t equals 0. So it moves right from 0 to 3. At 3 it's not moving at all though. So I got to use an open bracket at 3. It moves left where the velocity is negative. That's 3 to 8 because 8 is the endpoint on our interval. And the only time it's 0 is at 3, so that's the only one I can't include. It is moving right at 0 and left at 8. So this tells me when it's moving which direction. It's stationary where the velocity is 0 at t equals 3. I don't have units in this problem, so I can't tell you if it's feet per second or meters per second, just because there's not units in the problem. Well, let's try it again with another one. This is a ball or a stone being thrown in the air. A stone is thrown upward on a Martian cliff. The height of the stone above the ground is given by negative 6t squared plus 64t plus 192. And the first question is find the velocity and acceleration. And the first question is just asking me to find the derivative. The velocity is the first derivative, which is negative 12t plus 64. And the acceleration is the second derivative, or the derivative of the velocity, which is negative 12. By the way, negative 12 would be the acceleration on Mars. It's constant, just like the acceleration on Earth. The acceleration on Earth is negative 9.8 meters per second squared. Oops. And the acceleration on Earth in feet per second is negative 32 feet per second. So the velocity is the first derivative of the position function. The acceleration is the derivative of the velocity, or the second derivative of the position function. And part B says, when does it reach its highest point? Well, if you think about, this is a weird one. You have to really think about what's happening with the rock. But when you throw a rock in the air, originally the velocity is positive when you throw a rock in the air, because when you throw it, it's moving up. So all this time I have a positive velocity until I get to the very top. At the very top, the velocity stops. The velocity goes to 0, because what happens is the rock turns around and starts getting a negative velocity because it moves back towards the ground. That's a negative velocity. So where the velocity is 0 is where the rock turns around, and that happens at the highest point, because when it turns around, it quits moving up anymore and starts moving down. So to answer part B, to figure out where it reaches its highest point, I take the velocity and set it equal to 0, because at the highest point, the rock is turning around, and so the velocity stops moving. And so I get 64 equals 12t, and 64 divided by 12 is 5 1/3. So the stone reaches its highest point at 5 1/3 seconds, if that was the time unit. So that's when it reaches its highest point. To find out when a rock reaches its maximum or its highest point, set the velocity equal to 0. But then it says, what's the maximum height? Well, I know when it reaches its maximum height. So if I take that time and plug it into the function that tells me the height, I'll know. In this case, to find the max height, I have to plug it back into my position function, because that's what the position function tells me, the height off the ground. And so I replace every t in my position function with 5 1/3, and I figure out what y value I get, which will be the height of the rock. So I type this in. Oh, that should be squared, I believe. Oh no, yeah. And it looks like what you get is 362 2/3, or 362.7. So I now have the maximum height, and I also have when it reaches that maximum height. So to find the maximum height, we set the velocity equal to 0, and then we take that value for time and we plug that into the position function to figure out how tall it was. The last one says, when does the stone strike the ground? And if you think about it, the stone hits the ground when the height is 0. That's how you know the rock has hit the ground, because the position off the ground will be height 0. Well, the height is given by my position function. This tells me how high it is off the ground. So to answer part C, to figure out where it hits the ground, I take the position function, which is negative 6t squared plus 64t plus 192, and I set the position function equal to 0. because the position function tells me how high it is off the ground, and when it hits the ground, the position will be 0. So to solve this, it's a quadratic equation. I could use the quadratic formula. In this case, though, I can factor out a -6. I'm left with t squared. Oh no, that doesn't work very well. I'll leave it like it is, and I'll use the quadratic formula. This is a weird one to factor. It's possible to factor, I believe, but if it's not, I can use the quadratic formula. That tells me that t is -b plus or minus the square root of b squared minus 4ac all over 2a. My b in this case is 64. So I'm just going to fill in the a, b's, and c's. A is -6. B is 64. C is 192. And I calculate this. So we have 64 squared plus 4 times 6 times 192, because those two negatives will make a positive. That gives me 8704 under the square root. If I take the square root of 8704, I get 93.3. And then I just type these both in. Let's move down a notch. So there are two answers here. The first is -64 minus 93.3 over -12. And the second is -64 plus 93.3 over -12. And so I calculate these. -64 minus 93.3 over -12. The first one yields 13.1. And this is time, remember. And the second one, -64 plus 93.3 divided by -12, gives me -2.4 as the time. And we all know you can't have negative time unless you're traveling in a DeLorean. So in this case, the time is 13.1. That's how long the stone is in air, and that's when it hits the ground. 13.1 seconds, or whatever the time units are. So to figure out when it hits the ground, you have to go and set the position equal to 0. Because when it hits the ground, the height off the ground will be 0.